Hi PLF, this is your physics loving friend came again to explain yesterday's question. So before going to that, let me talk about a magnet. For example, let us consider a bar magnet which has two poles in it. Let it be North Pole and South Pole. So this magnet will create some region around itself, so which we call that as magnetic field. So this magnetic field will be created by their magnetic field lines. So these are the magnetic field lines. Magnetic field lines will be started from North Pole and ended at South Pole. For example, if you place a conductor or a metal nearer to this bar magnet, its magnetic field lines will be passed over or passed through this conductor. So that means some magnetic flux will be linked with this coil or conductor. For example, if we move this conductor either towards or away, then there will be some change in magnetic flux, right? So according to electromagnetic induction, whenever there is some change in magnetic flux, that is delta pi, there will be some induced EMF. So EMF will be induced in the coil or a conductor. So that induced EMF will try to oppose its cause. So which is mentioned as Lenz's law, right? So here, coming to the question, I have taken a copper tube. Through that copper tube I have dropped some objects like cylinder or a sphere, etc. Coming to the magnet which I have dropped, this magnet is falling down. So that means it is allowed to pass through this copper tube. Whenever it is allowed to pass through this copper tube, then the magnetic flux linked with this copper tube will be changed. So when there is change in magnetic flux, then EMF will be induced in this copper, so which try to oppose the motion of this magnet. So that's why it is taking somewhat more time when compared with remaining objects. So this is your answer. Thank you. One student asked me a doubt that surface area has any influence on that opposition. That means, let me tell you, for example, if this is the copper plate which is suspended from this particular point and it is being oscillated in between two magnetic poles. When it is oscillating, the magnetic flux linked with this copper plate will be changed. So whenever there is some change in magnetic flux, some EMF will be induced in it, which produces eddy current, and that eddy current will oppose the motion of this copper plate. So therefore the oscillations will be damped. What are damped? The periodic oscillations of decreasing amplitude are called damped oscillations. For example, if we have a slotted plate, for example, if the copper plate is having some slots in this way, so in this case the magnetic flux linked with the coil also changes, plate changes, but it is somewhat lesser when compared to the above case. So this is a different scenario. we can talk about this one, we can discuss this one later. Now let us talk about the important applications of eddy currents. So generally in our plus 2 in IP there is an important question, what are the advantages of eddy currents? In that we will be dealing magnetic braking of trains. So by using magnets we can stop trains. So generally electromagnets will be situated above the rails. When the electromagnets get activated, then what happens? Eddy currents will be produced, and those eddy currents will stop the motion of the train. So this is called magnetic braking of trains. So let's have a look on this magnetic braking of trains. So here is an apparatus. This is a 9-volt battery. This is a DC motor, and I have an aluminum plate which is fitted like this, and this is a magnet. So here it is rotating, and I am bringing this one. Its velocity is getting reduced. So in this way, strong electromagnets will be used in magnetic braking of trains. So suggest some concepts on physics, suggest some more concepts on physics, so that we will analyze it and make you understand in a realistic way. Thank you.